everyone, myself Sravanthi, working as an assistant professor in the Department of Data Science and Cybersecurity in MLR Institute of Technology. Today my topic is storage allocation techniques, or we can also call it as storage organization. So here I am going to discuss what is storage organization and what are the types of storage allocation techniques are there, like static allocations and stack allocations, heap allocations. All these things we are going to discuss with some examples. So first one, so what is storage allocation technique? So the storage allocation technique, we can also call it as storage organization. So the program or the thing what we are going to write in the memory, how it is going to be stored. So that thing we are going to discuss over here. There are different types of strategies are this. There are different storage strategies are there here. The first one is static allocation, stack allocation and heap allocation. The static allocation, so the name itself tells us that the static allocation is nothing but the storage is done at compile time. All the objects memory is allocated or storage is allocated at compile time, not at runtime or execution time. Coming to here, stack and heap allocation. So for these two, stack and heap allocation, the memory is allocated dynamically. The memory is allocated dynamically. Nothing but at runtime, the memory is going to be allocated. The static allocation is nothing but manages the runtime storage as a stack. So whenever I am in it, then we are going to allot the memory for it. Heap allocation. Heap allocation is nothing but it is mainly used for the dynamic memory allocations like MLOC, CLOC or realloc. I'm free. The memory will be allocated and it can be realloc is nothing but if again I'm in need of the memory, I can increase the size of it and I can delete the memory, I can free the memory. All these things are done here in this heap allocation. So nothing but these two things, stack and heap allocations, are going to be used in dynamic memory allocation. The static allocation is done at compile time. So we are going to discuss in detail of each one. So static allocation. So the static allocation is nothing but allocations are done at compile time, not at runtime or execution time. The allocation is done at compile time. Whenever in the program, if I am going to declare a variable of type static or normal variable, then nothing but the memory is going to be allocated at compile time. When the program is compiled, at that time the memory will be allocated. So here binding do not change at runtime. So binding do not change at runtime is nothing but once the memory is allocated, let us take this number in the memory code and this is suppose static. Here the memory is allocated for number. When some memory address is allocated for this number. So until the program execution completes, the memory is fixed for it. It won't change at runtime or execution time. When this program is executing, at that time the memory is not going to be changed. It is going to be fixed. It is the fixed memory allocation. Once the memory is allocated at compile time, the program until the program completion, the memory won't be changed. The address won't be changed. It will be fixed. Once the program execution is completed, it will be deleted from this and the memory is free. And when I compile the program, again the memory will be allocated. So nothing but binding don't change at runtime. The address won't be changed at runtime or execution time. Once the memory is allocated, it will be fixed until the program execution completes. One activation record per procedure. One activation record for procedure is nothing but when a function call is done, the activation record, nothing but some memory will be allocated in the memory. So nothing but when a function is called, one activation record will be created in the procedure. Nothing but for each function, one activation record will be created. So what activation record will do is nothing but when a function call is done, so it goes to the definition, nothing but where this function name, where this procedure is existing, it goes to that procedure and it executes, and all those things are going to be stored over here. Once the definition is completed, it deletes and it comes back to the function. Activation can have permanent lifetime in case of static allocation. Here the activation record, here I am telling that for every procedure there will be one activation record. So once the activation record, the memory is allocated. So here in static allocation, the memory is allocated at compile time. So this compile time memory is fixed, nothing but it is permanent until I complete this procedure execution. So nothing but if I call, or it will be, if it is a recursion function, the memory will not be allocated for it again and again. Why? Because once the function or once the procedure is called, some memory is allocated for it. Some memory is allocated for its static. And once again, the recursion is nothing but one more function is called. Again, I need to allot some more time. So, but that is not possible in static allocation. Why? Because here only for one function or for one procedure, only one activation record is created. If the same function is called n number of times, that much space is not will not be there here to give the to store that variables or to store that procedure. So that is nothing but here the permanent lifetime will be existing. So for these activation record, the memory is allocated, some address will be allocated. These address will be there permanent until the completion of this procedure. These address won't be changed here. So permanent lifetime in case of static allocation. So activation can have permanent lifetime. So what are the disadvantages here? The recursion is not possible here. Why the recursion is not possible? So the recursion is nothing but will be having it needs more memory. But here in static allocation, memory is given compilation time. Nothing but the memory allocation is done at compile time. But coming to here recursion, let me take fact of phi. Fact of phi is nothing but for this initially when it call, some memory will be allocated, some set of memory will be allocated at compile time when this fact of phi is compiled. But again, as it is a recursion, again fact of 4 will be called, fact of 3 will be called, fact of 2, fact of 1. So for all these, the memory will not be allocated. Why? Because only for one procedure, only one activation record will be created, and these activation record will be deleted, all will be completed only when this function execution is completed. So that is the reason recursion is not possible for all these things. Whenever I'm calling the same function, but the memory won't be sufficient. So that is the reason recursion is not possible in static allocation. Why? Because the memory is allocated only at compile time. Size of the data objects must be known at compile time. For example, let me take arrays. So initially when I am declaring array, I have declared the size as a of phi. A of phi is nothing but in the static memory, the memory will be allocated for a of phi. Nothing but some 20 bytes of memory is allocated. 20 bytes of memory is allocated. But when I'm writing the program or when I'm using, I want to use for a of 10. Nothing but 10 variables I need to use. But the memory is not sufficient. Only the memory is allocated only for 5 variables. The remaining 5 variables, there is no memory. So that is the reason we are going to tell this is one of the disadvantage over here. The size of the object should be known before only. If I give a of 5 and if I am taking a of 10, I am lagging with 5 variables. There is no space for 5 variables to store in this static memory. If suppose a of 5 and I'm using only a of 3, so that remaining 2 variables or nothing but 10 bytes of memory is wasted over here. So these are the disadvantages of a static allocation. Data structures cannot be created here manually. Why? Because here the dynamic memory allocation is not going to be done in static allocation. So the static allocation is only fixed for the compile time. When the program is compiled, the memory is allocated and only the memory will be allocated over there. Once the program execution completes, then the memory will be free. Stack allocation. So here the stack allocation, the name itself tells us the stack allocation is nothing but it supports a FIFO principle, that is LIFO principle, that is nothing but last in first out principle. It follows last in first out principle. LIFO principle, it follows stack. So whenever a new activation begins, activation record is pushed onto the stack, and whenever activation ends, so it is popped off from the stack. A stack is like this a container. Whenever a function call is done, nothing but whenever a function call is done, one activation record is created. When one activation record will be created, nothing but for every procedure or for every function, the activation record will be created. When these execution is completed, these will be popped off. Nothing but whenever the procedures are called, it will be stored in the stack. And whenever the activation ends, nothing but this particular function execution is completed, nothing but it is popped off. Let me take here fact of phi. Fact of phi is nothing but initially fact of phi, it will be stored, next fact of 4, next fact of 3, fact of 2, fact of 1. Fact of 1. So once this procedure, whenever the activation record, whenever the function is called or whenever the procedure is called, activation record is created. So in this way, these 5 activation records are created. So once the top one will be execution will be completed, nothing but the fact of 1 execution is completed, then it will be popped off. Then it will be popped off. Then the next one will be popped off. So that is here. Whenever a new activation begins, that will be stored in the on the stack, pushed onto the stack. And whenever activation ends, the activation record will be popped off. Nothing but it is going to be deleted from the stack. So local variables are bound to fresh storage. Local variables are bound to fresh storage is nothing but here fact of 5 is nothing but where the n variable is 5, where the n variable is equal to 5. Here the n variable is equal to 4, and here the n variable is equal to 3. Here n variable is equal to 2. Here n variable is equal to 1. Every time it is pointing to the fresh local variable. Here n equal to 5 is there when fact of 5, nothing but it is fact of n. Fact of n is nothing but initially it is 5, and n minus 1 is nothing but it is pointing to fact of 4, n equal to 4, and the next n minus 1, nothing but 4 minus 1, 3. So in this way, the every time the local variable n is updated to the fresh storage, nothing but it is bounded to that particular procedure itself. This n equal to 5 is not given to all the activation records. In each activation record, there is the new local variable that is nothing but some n value. Recursion is possible. See here, the recursion is possible. As stack supports the recursion, why? Because here the memory is allocated dynamically. Here the memory is not allocated statically. Nothing but at compile time, the memory is not allocated. At runtime or execution time, we are going to allot the memory. Activation can have nested lifetime in case of static allocation. So what it is happening here, the memory, the activation in the static allocation, the activation record is permanent. Coming to here, nested lifetime. So here this fact of 5 is a combination of fact of 1, fact of 2, fact of 3, fact of 4 and fact of 5. It is a nested lifetime. When the program execution completes, when these activation record completes, it will be popped off. Nothing but it is nested. It is depending on one on the other. So that is why we are going to call it as nested lifetime. Disadvantages. Local variables cannot be retained once the activation ends. See here, when I am going to do this fact of 1 activation record, it is going to produce me value as n equal to 1. To do this fact of 2, I need the previous one. The popped one value should be used here in this fact of 2. So that is not possible here. This is the one disadvantage here. Local variables cannot be retained once the activation ends. So fact of 1 is completed, then it is popped off, but this value is not used in the next activation record. So that is one disadvantage here. Dynamic data structures are not going to be supported here. Actually, it is supported by the system, not by the user. So the next one is heap allocation. Here the heap allocation is nothing but the allocation and deallocation can be done in any order. Here, when I'm going to discuss the heap allocation, the memory is going to be allocated, dynamic memory allocation is done. Nothing but I can use malloc or calloc or realloc or free. So the memory can be allocated by using malloc, or it can be allocated by using calloc, or if the memory allocated which is not sufficient, I can realloc. Nothing but I can increase the size of the memory or I can decrease the size of the memory. Once the execution is completed, I can free that space also I can free. So that is nothing but here the allocation and deallocation can be done in any order. So based on the question or based on the program, memory will be allocated, deallocated, and it can be done in any ways. That won't be known to us. So activation can have arbitrary lifetime. So here in static allocation, the memory is allocated for activation record. The memory is allocated permanently. Nothing but once the program execution completes, then only the activation record will be removed. And coming to the stack allocation, it is a nested lifetime. It is why? Because the recursion is following and activation records are placed over there. When one activation record completes, one is depending on the other. It is a nested lifetime. Coming to here, activation can have arbitrary lifetime. So nothing but here, whenever the program execution is completed, it will be free. So when it is free or when it is allocating the memory or when it is deallocating the memory is not known to us. So nothing but it is a arbitrary lifetime. It can be allocated, and if the execution or if that part of the activation record part is completed, then it will be free. So it is done at any time. Recursion is supported. So the factorial which we have seen here, the recursion will be supported over here. Dynamic data structures are also supported here. We are going to do using dynamic data structures. So the disadvantage here is heap management is overhead. So heap management is overhead is nothing but here I'm having some plenty of activation records are there. Plenty of activation records are there here. When I'm using these activation records for fact of 5, fact of 4 or fact of 3 and fact of 2. Once these activation record is completed, I'm popped off, but this memory is not removed until and I use these free or until I use this dynamic memory allocation free, then only the memory will be free. If I don't use these free, then the memory will not be removed here. So if the memory is not removed in the CPU, in the RAM memory, the memory will be allocated for factor of 2 in the same way until and unless I free that space. So that is nothing but heap management is overhead. So if I won't free this space, then this is still it is there in the memory. In the same way for fact of 3 also, for fact of 4 also, for fact of 5 also, all the memory is there here. When one more function or when one more program comes for execution, this space is totally filled with these activation records. So nothing but here the heap management is overhead. So this is about the heap allocation here. So here we have discussed about the storage allocation, how we are going to allocate the memory how we are going to allocate the memory. There are different strategies are there, different storage strategies are there. Static allocation, stack allocation and heap allocation. So static allocation is nothing but which is going to be the memory is going to be allocated at compile time. It is not done at runtime or execution time. Coming to the stack allocation and heap allocation, the memory is allocated dynamically. Dynamically at runtime, the memory is going to be allocated here. In static allocation, activation records will be created for only one for procedure. Their recursion is not possible. Coming to here stack and heap allocation, the memory recursion is possible. Here the memory is allocated at any time. There the memory is fixed, and if you want to increase the size of that one, it is not possible in static allocation, but that is possible in stack and heap allocation. Here the arbitrary lifetime will be there for activation record. Coming to the static allocation, there will be permanent lifetime, and coming to the stack allocation, it is a nested lifetime. So these are the differences for the stack and heap allocations. Thank you.